so that you'll have a record of it. I'll send you the recording after it converts over to YouTube. So
Thank you.
You'll have a chance to see that. When you are doing probability or statistical calculations of any of the things that we've done, mean, median, mode, standard deviations, etc., there are formulas that are used by Excel. We find them here under More Functions in Excel. And then there's a list. We get several. Statistical are some of them. And this list is quite lengthy. Now, there's a couple of things to understand. We talk about mean. Mean is called by Excel the average. Even though statisticians dislike that term, Excel uses it. So that is the mean. And if we want to have the mean of any set of data, if we simply click on that, what comes up next is a little dialog box that allows us to specify the range that we are interested in. And in this case, what I want to do is take the mean or the average of client age. So the way to put that string of data in is simply highlight it. And it will then bring it over. For the second part of this argument, we generally ignore unless we're only interested in the mean of a subset. So then we can tell how many of the arguments that you're going to average. Now, generally speaking, we don't use that, so I wouldn't worry about it. So you'll see a couple of things. You'll see a number here and the formula result down here, but there's nothing printed yet in the box. If we say OK, it gives us the mean of the client age, in this case, 34.65. And remember the rules about rounding. For data, we go 1 decimal place further to the right than the basic data. So this would round off at 34.7. Does that make sense? So yes. Excel doesn't recognize those rules very well. So we have to do that on our own. But if you just provide the Excel result, that's really what we like. So let's go and look at others. You were also supposed to calculate the median. So if we go down here, median is one of our functions. And it pulls up. And again, if we simply highlight the range of the data that we're working with, we see that the median can be calculated at, no, that's, what have I done? That's not right. Oh, here's another thing. It simply added it to the average. So what we want to do is actually get rid of that. That was my mistake. I do that. I forget that you have to be in a different cell. That's another part of Excel. Generally speaking, if you just type in a cell that's occupied in Excel, it'll erase what was there originally. Not with these things. It adds the formulas together. So we'll do the median again and do the highlight, and we get 35. Well, 35 is close to the average, but let's see what happens if we do the same thing with the wait time data. And this time we're going to include all of the information. When you did this in the assignment, you did everything correctly, but I know you didn't know how to use the formulas. So let's do the same. We'll do the average of this range and come up with an average age of, or an average wait time of 59.05 minutes, or almost an hour. Now, if you look at the data, of course, we've got a couple of very large numbers. The issue with data is that you don't reject it unless you can provide a rock solid rationale. And unless we happen to know that these are in error, and one thing you pointed out, this is 10 hours, 600 minutes is 10 hours. Nobody's going to wait in a waiting room for 10 hours. But if we go back up here, 160 is 2 2/3 hours. Quite frankly, I've never waited that long in a waiting room either. Usually, as a matter of fact, within a half an hour, I'm at the desk saying, when am I going to be seen? And unless the doctor is saving a life, I insist. And so most people will do that. So these may or may not be errors. And we don't know if they're errors because they waited a long time and just wrote down a number out of anger, or if they're input errors into the database. We don't know. Unless we can prove it, we have to include them in our calculations. But then let's look at the median of that same data set. And this is where, when you have outliers, this is where the median, obviously, as you know, is a much better measure of the center of a data set than anything else. And all of a sudden, it's dropped from 59 to 19 minutes. And this, if we look at these two as being really outside the norm and just sort of glance at some of these figures, that's not an unreasonable number. But as I said before, we can't ignore them. Now remember the standard deviation. Anytime you're calculating a standard deviation, you have to include all the data. And that means including the mean instead of the median. We could order this data and exclude these using one of these functions, but we're not going to do that. But we will look at what the standard deviation here is, and we'll go through that same thing. So let's go over here, and we'll go down to standard deviation, SDev, or STDev rather. And we have two choices. We have stdev.p, which is for a population. That would require that we surveyed everyone that was a client at the office. But if our population was only those that had come in on a specific day or a specific week, we could use the population calculation. Remember, it's slightly different in that we calculate the same thing, the difference between the data points in the mean squared, and then the sum of all of those differences squared, divided by the total number of data points if we're looking at a population. Whereas with a sample, and we're going to assume, unless you are told otherwise, always assume a sample. A sample is a subset of the population. And this may be just a random series of people taken during a week. We don't know. We have no information as to how these particular patients were chosen. So I would assume standard. Remember, or a sample. And remember, the difference is that we calculate the differences between the mean and the data point and the mean. And then we square each of those, because if you will have negative numbers and you want everything to be positive. And then we divide it by one less than the total population to make it a much better predictor. And that's really what we do. It's a better predictor of how it would scale up to the entire population. And there's a lot of arcane statistical reasons for that we won't go into. But that's the standard statistical approach that we use. So if we want to use the standard deviation using a sample, again, let's do the same thing. And what we have is a standard deviation of 132. Now, I'll tell you from my own experimentation, the standard deviation drops significantly if we remove this 600. We only would calculate that if we could justify not including it. And if we further remove this other one, which is way far outside the norm, remember the median here is 19. So 160 is way outside that, that median. If we remove both of those, this standard deviation drops even further. But again, to do that, we have to justify it. So in the absence of any reason or any request in a problem to justify such a thing, use all the data as given. Assume that it's real, even if some of it looks completely ridiculous. Note that this person and this person, the two with the biggest numbers, both put down number 1 or no for satisfaction. So yes, if they waited a long time, they probably were dissatisfied. So there's at least we can look at that and say, well, maybe they waited that long and maybe this was just what they estimated. Who knows? But the data are there. So does that make sense for how we use these functions?
Yes.
Okay.
Yeah.
So let's go down and look at a few more that we may have run into, and we will be running into in the rest of the class, the rest of the mod. One is we'll be looking at let's see, the intercept. This is, remember from algebra, the equation for a straight line. Y equals mx plus b, where b was the point of the line, or the point on the y-axis that the line crossed that axis. Remember that?
A little bit.
Okay.
I'm sure it'll come back to me quickly.
We'll see it next week when we do regression analysis, because one of the things that we do is we try to take data and make sense of it and see if we can make it fit in a broad sense, some sort of linear relationship. Data are all over the place in many statistical studies, but the y-intercept is something that we can calculate. Mode, we'll go into mode. There's an easier way, in my opinion, to do mode in a small data set like this, and I'll go through that in a bit. But remember, the mode is those data points that have the number of data points that have the same value. The value that appears the greatest number of times in the data set is the mode. And you can have two modes if you have two values that appear the same number of times. And there's two ways of doing that. We can use the mode multi and mode single. That will they both will return pretty much the same thing. So let's just do a mode on this satisfaction scale, and I'm going to use the mode here, and our satisfaction scale is that range, and the mode is well, I did it again. All right, we can fix that. I didn't like that. All right, we'll just get rid of that. And try again. That's one of my favorite tricks, is to forget to erase the stuff. So we'll do that, and we'll highlight again, and we'll come up with an answer. 1. Well, if we just sort of look at this list, it looks that way. But let me show you another way to calculate a mode. And I'm going to do that on the wait time data. And what I'm going to do first is simply copy that data range and place it into a different location. And then I'm going to come over here to the data and sort it from smallest to largest. And it's going to do that. And then we're going to look at this and we're going to see that we have 3 10s, 3 15s, and 3 60s. So those are our modes in that data set. So we can see this by simply looking at it at this point. And you did that correctly. You went and counted up the data. But there is, this is another quick way, if it's not real obvious, of how to do that. Just another idea. And this tells us that, again, we had 3 modes because we have 3 data values that appear 3 times each in the data set. Okay. So there are some tricks we can use. Okay. So let's look at a couple of other of these formulas before we go into probability, which is this week's fun subject. I like probability. It's a lot of fun to play with it. So we're going to go in again here. You'll see several others. One of the ones I wanted to get to is quartiles. And quartiles are a way of describing data that allows us to determine whether we have true outlier data, meaning data that are very, very far away from the bulk of the data set. And one of the ways to do that is to set quartiles. And quartiles merely divided into quarters. Okay, so if we look at something and divide it up into quarters, what we have is let's just take a look at the wait time. We have 20 data sets, so each quarter is going to be 5 of those data sets. So the first quarter will comprise these 5, the 5s and the 10s. The second quarter will comprise 15, 15, 15, 16, 18. And that ends the midpoint here between data point 10 and 11 is also the median. This is another way of looking at median. You can line things up and simply count halfway through the data plan. Remember, the median in this data set was 19 minutes. And since the median falls in between data points 10 and 11, because we have an even number of data points, we add them up and divide by 2. 38 divided by 2 is 19. So it's midway here. So the start of the third quarter is here, and we have 1, 2, 3, 4, 5 data points. And then the last quarter is these last 5 data points, 360s, the 160, and the 600. So that's something that we use to determine outlier status. And what we do is we talked about that. I put up an illustration about box and whisker plots, did I, last time?
Yeah.
Okay.
I think so.
Yeah. And so there's what we call a 5-number summary, which is the minimum data point, in this case 5. The beginning of the second quarter, in other words, the end of Q1. So that would be this 15 here. The midpoint, that's Q2. So we've got we've got the box itself has boundaries, and boundaries can be calculated midway between data point 5 and 6 because the actual boundary is between these two. So that would be a 12.5 value. And then the midpoint, the midpoint between 18 and 20 is 19. So that's, we already know that's the median. And so the definition of Q2 is the median. That's the end of the second quarter. Q3 ends here. Unfortunately, it ends midway between 30 and 60, which is 45. So we have a range of 45. We have something called the interquartile range. Remember that? Between the top of Q3 and the top of Q1. So 12.5 plus 45 in this case is going to be 57.5. So the interquartile range is 57, is the difference between 12.5 and 45, or 32.5. So what we have is, remember that if we then calculate 1.5 times that interquartile range, we said that was 32.5. So half of that's going to be 16.25. So if we add that up, 48.75. If we are, if a data point is beyond 1.5 times the interquartile range, either below Q1 or above Q3, okay, then we consider it an outlier. Now, outliers are not totally ignored. They are noted, but we don't use them for certain other kinds of calculations, and we won't get into those. We don't have time in this particular course to get into some of the more abstract calculations involved in statistics. But if we look at the top of Q3 and then go 1.5 times the interquartile range, or 32.5. So we add 48.75 to that, we're going to get 93.75 as 1.5 times that interquartile range. And if we look at 160 and 600, both of them are significantly more than 93.75 beyond the third quartile. Okay, so we'd subtract that third quartile value, that boundary 45, from 160, we get 115, way more than 93.75. And if we subtract that from 600, that's even further out. So we would consider as statisticians that these are outlier values. And what that would prompt us to do is see if we can exclude them. If we can't, we show them, but other calculations would not include them. So that's another way of doing quartile ranges. But let's just look at the quartiles. Using the quartile function, we can actually calculate the quartiles. And we go to quartile, and what we want to do is calculate the first quartile. Oh, it didn't like that. Oh, it doesn't like that function. I got the wrong one. Excel can be tough to figure out some of these. We want the inclusive. We want to include all of the data. So the array, and we didn't put in the array. So we want the array, and we want the first quartile, and we get 13.75. Okay. Now there's a reason that doesn't quite work out to be the 12.5 that I estimated, but it has to do with some weighting that's done with this. So let's go to the second quartile, which we know is right here. Do the same thing. And I'm going to try this as well and see if we get the similar answer that I wanted. And that's a 2. So we get 19. We got 19, which is exactly what we expected to get, the median of the data set. And in fact, when you do quartile 2, it may actually default to calculating the median. I'm not quite sure of all of that. So let's go down here and go and get the third quartile. If this seems like a lot of work to get this information, think about what this would take if you had 1,000 data points.
Yeah.
Right? You really want the ability to use this. Now, big studies like the pharmaceutical industry and others will use the SAS Institute, which is Statistical Analysis System Institute software, which is very expensive to lease, but it can deal with hundreds of thousands of data points. And that's what many of them use. And it's much more sophisticated than Excel. Excel is pretty good when you've got less than 1,000 data points to deal with. You get up into the 10,000 range and Excel becomes very, very cumbersome. So you want, if you have a big data set, you're going to use something like the SAS Institute's group. Okay. So there we calculate, I calculated 45. So I used the
Exclusive?
Go ahead.
Exclusive or inclusive?
Pardon? Did I use exclusive or inclusive? Okay, yeah, let's use the inclusive this time.
Okay.
And see if we get a different answer. You know, part of the problem is that Excel does not do a good job of explaining how to use these or when you would use one. So we get the same answer. So it's a weighted system that they're making use of somehow. They do not explain how to do this. So the interquartile range here, there's no way to calculate that in Excel because, of course, it's only the difference between the Q3 and Q1. So we would simply do that following the standard Excel procedure of equals, let's see, that's L16 minus L6.
6.
And we get 23.75. Okay, so that's our interquartile range. So when we're doing our test for outliers, we'd multiply this by 1.5. Okay, so we're going to do that equals N11 times 1.5. So we get, no, should have been times N11. Naughty, naughty. A little frazzled. 35.625. So we'd probably could just call that 35.6 again, because we have no decimal points in our data. So again, this is obviously these next data points, the 60s, are not more than 35 off of the interquartile range. So, but this 160 and 60 are. So we can do this in several different ways. But sometimes we just have to remember some of these calculations are too simple. Remember we talked about the coefficient of variance being the standard deviation divided by the mean? Well, you don't get that in the statistical formulas because it's a simple number. You have to calculate the other two anyway. So it's not a problem. They don't put that in. So there are some things that we just get to do by hand, but they're generally one-step calculations. So that's the major functions. Let me just see if there's anything else that I can. We'll deal with correlation coefficient next week. By the way, I do currently plan to be back at school on Thursday of next week. I will let you know if that plan changes. But right now, I don't see any particular reason it should. So, you know, I might get fooled. My father has fooled us several times, but he's not coming out of this one.
Yeah, hopefully
yeah,
be okay.
Well, he will. I mean, he will pass, and that will be good for him, because he just is. He's he's just completely out. He's unconscious. Remember the slope of data. Here we have the slope of a straight line. You know, basically how much it goes up or down from horizontal. From the algebra class. Gee, is that a year and a half ago now? Probably.
Yeah, I think so.
Yeah. So you might want to go back and just take a quick look and refresh yourself. We'll go over that some as well next week and refresh that particular concept again, because it is used quite a bit when looking at data sets that seem to parallel each other. So anyway, we'll see those. Remember, variance is simply the square of the standard deviation. And again, we can do variance in a population or variance in a sample. And that's why it's critical to remember to find out if you're doing population or sample, because of course the calculation of the standard deviation and the variance itself, you calculate that first before you take the square root. You will you need to determine that because the denominators are different. So you do need to know whether you're working with a sample or a population. If the problem does not specify something that tells you that you're dealing with a population, always assume sample. You'll see this on your final. So be careful when you're taking the final. You'll be calculating some standard deviations and some variances. So read the question carefully to see which one of those calculations you're supposed to use. And you'll probably see that in this week's assessment as well. So, it's a subtle difference, but it will give you a different answer that the test will count wrong. So keep that in mind. I think we'll just, okay. I think we'll let this go for now. I just want to take a look. Number permutation, good. We'll get into that in a bit too. And they don't go into combinations. All right. So is that helpful?
Yes.
Great. So let's switch gears. And I'm going to switch back over to back to the shell here. And let's look at probabilities this week. Probabilities are covered in, if we look at the readings and tools, they're covered in chapters 2, 3, 4, 12, and 13 in the PDF, the OpenStax text. They're also summarized fairly well, and I'm going to base most of today on the Triola text that you have access to in the shell. as the ebook for the course, and that's chapter 4. We'll spend most of our time in chapter 4 on probability. So both of those work. Also, we have a couple of videos, a couple of other things that you can look at. There's this Khan Academy video looks at something that you will be looking at later in this week in combinations and permutations. So we'll go into those on Thursday. I do plan to be able to have class with you Thursday, so we will do that then. Because I'd like you to get started on some of the other things. Go ahead.
That video is for our discussion, or I mean our daily checkpoint for the last 2 days.
Oh, that video has been involved in it?
And the one for and the one for absolute zero and factorials.
Right.
So I already watched both of those.
Good, excellent. I'm glad you've watched them. That puts you a little ahead. So you know what a factorial is. So, and that's that's important when we get into permutations and combinations, because we use factorial calculations in those exclusively. And as you may have seen from let's see, in here in that video.
Yeah.
So we'll get into that too, and maybe explore some of that. So let's go back into here. The probability is the discussion, the use of probability. And again, the usual discussion for this class, pick a scenario, and whatever one that that makes you kind of interested in looking at it. So, but we'll talk about what probabilities are and what they aren't in just right now when we get started. So, and again, you have your assignment. Let's take a look. Assignment here, I'm going to warn you to watch out for the assignment right away for the simple reason that there's some stuff in here that we won't have time to discuss tonight. Wake up, computer. There we go. So I don't know if you've looked at this one yet or not, but there's there's some issues here that we'll go through tonight in some more detail, but combinations and permutations we'll get to later in the week. Next week, we'll actually get into regression, even though they have mentioned that in the title here. Let's see. Wait a second. I didn't share that. Yeah, here we go. Now you can see it. So here we're going to be looking at this first question actually, and the second question actually talk about this correlation coefficient, and we'll go into that, I think, on Thursday, if that is okay with you.
Yeah.
So the rest of it we'll be covering some things here that cover these particular ones. Don't think I need to worry about you and factorial, since we just discussed that you've already done that. So let's go back to here we go. So let's pull up okay, I don't have that up yet. Okay. All right. So I'll pull that up in a moment. Here we go. Now here's an example where we're looking at correlation.
Wait, Mike, you have to share it.
Oh, sorry. Thank you for reminding me. That better?
Yeah.
Okay. So I'm going to enable editing on this because I want to do some things here. Here we go. So this is what we call a dot plot. And a dot plot just allows you to put the data points into a grid. Okay, an XY grid. So we have these data points. We have two arrays of data, X and Y. And from those, we can do certain kinds of calculations. Now, in your instructions, it tells you to use trend. Don't. It's frustrating. I have finally figured out how to use it partly, but it's very poorly done because it just won't return any useful data. So this is where you really need, if you take a look at this, the bulk of the data, we've got data all over the place. We've got a couple of things here where we have the same value of X and two different values of Y. In fact, we've got that in at least two spots in this thing. Three spots. We've got the same value of X and two very different values of Y. Let me give you an example of what this might be. A number of years ago, a study was published talking about the difference between correlation and causation. And that's going to be really part of the topic of next week. But they looked at the price of a slice of pizza in New York City and the price of subway fare in New York City. And they found that they both followed the same upward trend. So every time the price of subway fare went up, so did the price of a slice of pizza. Or the other way you could look at it is that every time the price of a slice of pizza went up, so did the subway fare. Now, it does not make any sort of logical sense that the price of a slice of pizza would cause subway fares to rise, but they correlate. So the question a statistician asks is, would it make sense to think that these two, one thing could be causing the other? And this is a big problem in our society. People don't understand causation. They think because two things happen, they must be related. And in the case of, this is a good example of why that doesn't have to be the case. Because of course, what you're really looking at is the effect of inflation. When they take that data and correlate it to inflation, then that seems to be what you'd expect, actually, as the causative agent of those changes. But nonetheless, and that's a trivial example, but it does work. But you can get data like this, and all, and plot it out. Pretty obvious that there is a general trend upward, even though we've got two values of X or two values of Y at very different values of X as well, and two values of Y over here that are at not very different values of X. So it's not perfect. This would indicate that whatever this data is derived from is correlated, but not necessarily in a causation way. In other words, one of them is not actually causing the other to change. Okay, so we can look at these. This is what you're going to be looking at. But as I say, let's wait until and work on problems 1 and 2 when we have a chance on Thursday to discuss the use of these other aha, we have our friend.
Did you throw something down the stairs? Are you lying? I think you are. What do you say? Sorry for what? Don't throw it. You could break it. Throw it away. It's trash if you break it. Do you understand? Watch the TV, please. And go play with your book, please. Sorry.
No problem.
He threw it downstairs. I know he threw it downstairs. I heard him.
Yeah.
It's his little leapfrog. Did you ever have like a leapfrog learning pad when you were a kid?
Yeah.
Yeah.
So it jumped down.
I got him one last Christmas. Yep, it leaped on down the stairs. Monster. Oh, kids.
But
okay.
yeah.
Sorry. Go ahead.
That's no problem. But you can see part of the assignment here is going to be calculating some parameters of this, the slope and the intercept of this line that would best describe this change. And then you can draw it. So we'll get into that. But as I said, trend is confusing. I spent a great deal of time last mod teaching this class, trying to figure out how to use that. And they tell you that's what you're supposed to use. If we look at the formulas here, if we go to trend, the description is it returns numbers in a linear trend matching known data points using what they call the least squares method. That doesn't matter. The method doesn't matter. This just is very, very delicate to work with. So we'll go over that as well on Thursday. But I just wanted to get you to take a look at what was going on with this. So let's go back to,
okay.
Go ahead. Fine? All right.
No worries. I just said okay, sorry.
Great.
And I think he's playing with his leapfrog.
That's all right. I don't mind kids in the background at all. I don't mind them in the foreground either, for that matter. So anyway, I think what you'll find is that if you study the material this week, you'll be able to get most of it, and we'll work on the latter part of it on Thursday. So let's go back up to here, and of course you have an assessment. So let's talk about probabilities. And again, we have some definitions. An event is any result or outcome of anything that's done, whether it's a toss of a die or a clinical trial to test a new drug. The event is the result of that test or that procedure. Simple event is something that can't be further broken down. Rolling a die, it bounces and it comes up either anywhere from 1 to 6. So those are simple events. And then a sample space consists of all possible simple events. Well, in rolling a die, there are 6 possible simple events. Okay. So, and here's another way of looking at it. Births of boys and birth of children. They're either going to be a boy or a girl, so if you're looking at a single birth, the birth of a girl is what we call a simple event. If the birth of a boy would also be a simple event. And in fact, there are simply 2 simple events. So it's a sample space of 2, a boy or a girl. But if we have triplets, say, or 3 births, say, or just think about the report, Thanksgiving report of how many, 12 sets of twins born in the same hospital the same night.
Wow.
Yeah, that was a busy night.
Yeah.
For the OBs. So, in that case, if you got twins, you got We got three possibilities. They can both be girls. They can both be boys, or you can have one of each. Because all they said was twins. They didn't say identical. So they, you know, they could have been fraternal. So three possibilities. Girl, girl,
Mom,
boy, boy.
what are you doing, Mom?
Oh, baby. Shh.
Yeah, school.
So in these cases, okay, if we're looking at, say, three single births, we're not looking at triplets here. We're looking at three single births. There can be three boys, two boys and a girl. And these are single events. Two boys and a girl can occur. And if you're looking at the births as sequential events, you can have two boys, you can have three boys, two boys and a girl, two girls and a boy, or three girls. But if we look at them as things that can happen in an order, and where each of the three sets of births can be a different order, then we can come up with actually 8 different possibilities, ranging from boy, 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 girl, boy, girl, boy, boy, girl, girl, etc. All these different lists here in this thing. If we look at these 8 simple events, because we're looking at the likelihood of any combination of any unique order of these births. Okay, so these are and in this particular case, the way the data are presented, each procedure is these 3 births, whereas a single birth is its one procedure. 3 births would be 3 procedures. It would be each set of 3 would be one procedure, so it can happen in any of these orders. So again, it's all about definition and all about understanding exactly what you're looking at. So let's look at some notation. First off, capital P denotes a probability. And then we can use almost anything else to define the specific event. Sometimes we'll name it. If we're talking about, say, the probability of rolling a 6 when we roll 1 die, we would denote this would be probability of 6. So the probability of an event occurring, and in general, we're going to call that A. So we pronounce this P parenthesis A close paren as P of A, probability of A occurring. Okay, so when rolling a die, we can calculate the probability of a 6. And we would call that P of 6, or P parenthesis 6. And we can calculate that. There are 6 possible results. 6 is, and a 6, so it's 1 through 6, obviously. A 6 is only one of them. So the probability of rolling a 6 just randomly is 1 in 6, or 1/6. Probabilities are expressed as fractions, or decimals, or percentages. And remember, fractions, decimals, and percentages are interchangeable mathematically, right? So if the probability of rolling a 6 is 1 in 6, or 1/6, if we divide that, it's 16.7%, or 0.167. Probabilities, you have to be careful with probabilities. In that a lot of people will quote percentages. As I said, the probability of a 6 then would be 16.7%. Many other people prefer to use decimals. And one of the reasons that we're going to get to pretty quickly now is that the probability can be calculated by simply looking at the number of ways the event can occur. The specific event result can occur out of the number of different possible results. So in dice, it's easy. You roll. You have a one. You have to roll a 6. You've got one chance out of 6 possible outcomes. The die will not land on a point or a side or a corner or an edge or anything. So it will always land a flat side up, and we're always talking about the face that sticks up, okay? So the probability is, and the thing you have to say, if the dice are not loaded, any of those is equally probable. So the probability of rolling a 6 is exactly the same every time you roll the die of rolling a 2 or 3 or any other number. So we can calculate the probability of an event. So I'll let you take a look at some of these other things, but the issue is what I've done is what we call a classical approach. What I've done is recognizing that there are 6 possible outcomes of rolling a die, period. There are no others. And so when you do that, you can calculate that and figure out that that's just 1 in 6 of rolling a 6 on any one roll. There are others. We can use relative statistics, and we do this when looking at automobiles. When you look at Consumer Reports, the safety material there is all looking at the number of events reported. You remember the Consumer Reports will rate automobiles on the basis of the engine performance and mileage and other things. These are all things that basically they've gotten a huge number of data points, and then basically related that to the likelihood that your car is going to suffer, a fuel pump failure in the first year, for instance. So we can do that. That's called relative frequency. It's generally based on past data. Subjective is when we just, basically stick our finger up to the wind and make our best guess. And we hope that the subjective is being done based on having some knowledge. So this example of the probability of a passenger dying in a plane crash is not one I want to think about today, since I have to be on a plane at 6:45 in the morning. But pretty small. I mean, is really, really small. 1 in 10 million. This is, if we just take a look at that number, it's pretty small. So flying we feel safe, and it is. But we also need to know that using things like the relative frequency calculation and even going back and using, what did we call it? The classical approach of just calculating the possible number of outcomes, assuming they're all equally possible. So any of these are, especially the frequency approach, is an approximation, because of course you can't, your car You know, you may buy a car that has a 5% chance of a fuel pump failure in the first year, and you may drive it for 10 years without a single problem. And your neighbor may drive his for 1 month and lose a fuel pump. There is no way that we can really say that we can make any real predictions until we have something called deal with the likely thing called the law of large numbers, which is that means that if the procedure is repeated many times, then the probability of an event tends to approach that actual probability. But let's take a look at rolling a die. People go up to Black Hawk and Central City and do this all the time, and they're playing probabilities. Or you're looking at the probabilities of perhaps of winning the lottery. You know, good luck on that one, because it's very small. However, the person that wins it had 100% success for that purchase. But we can, if we're rolling dice, the first time we roll it, we might get a 3. Then, the next time we roll it is it might be a 3. In fact, you have the same possibility, 1 in 6, but 5 of the possible outcomes are not 3. So you have a 5 in 6 probability of not having a 3. Does that mean you won't? No. You can have a 3. You can roll a 3 5, 6, 7 times in a row. And that is and when we get into probabilities a little bit more, any probability we can calculate, if you do enough tries, will happen. But you may have to do 10 million tries to get a get something as repeated as often as you want. But if this assumes this assumes that we have enough data when we look at this law of large numbers. The fact is that every time you do a trial that has like a set of likely outcomes, each of those is equally possible each time. It's just that over time they'll average out, and over trials. Okay, so you can't. You can only hope that the one outcome will give you what you want. We can't look at things if we have to know, if we want to assume that that outcomes are equally likely, we need to have a basis for that. If we cannot have a basis for deciding the probability of any event, then we cannot apply a lot of probability rules to it. So we won't be going much into that. But let's just take a few other examples. Smoking. This was I can't remember the date on the Harris interactive survey. I think this was in about 2014, maybe 2013. Surveyed over 1,000 adults, 1,010, 202 of them smoked. The probability that a randomly selected outcome, or a randomly selected adult in the United States is smoking, if we look at the number of smokers divided by the total number of people surveyed, very conveniently, this comes out to be 0.2, 20%. Okay. So we can't just assume that that the next person we're going to find, there is a reduced probability that this person will be a smoker. But note, 20%, that's 1 in 5. That does not mean that you have to go find 5 people before you're going to find one smoker. You may have to find 10, or you may find it the first time. So it's very difficult to infer what is likely to happen next when the 2 outcomes, which if we look at it, 20%, that means that there are, for every smoker, there were 4 non-smokers. So they're not equally likely. So it's difficult to put a number, to put much into this, other than if we have a large enough database, we can assume that if we scale it up further, that the population, 20% of the population smokes. So I'll leave it to you to look at the probability here based on the preview of this chapter talked about drug testing, I think probably for marijuana, and there were 1,000 subjects tested. 86% of them tested as not having any drug on board, and as claiming that they were non-drug users. So out of 1,860 of them claimed to be non-drug users that did not test positive for drugs. Well, at the same time, that left a bunch of people, and it also turns out that 6 of those 1,000 that tested positive, but said that they were non-drug users. And in further testing, it was found out that they were non-drug users. So we can have false positives. We also had something like 90 who were false negatives. They claimed to be non-drug users, and or they claimed to be drug users and tested as positive. And so it was they claimed to be drug users and tested as not drug users, false negatives. So we can have some that example is a good one that talks about what can happen when we do these kinds of analyses. We have to be confident that our methods are going to work as well. But using the classical approach, which is calculating the number of possibilities, we have, remember we had the 3 births, and we had 8 possibilities of boy, 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 girl, girl, girl as the extremes, and in between. These are all equally likely, because there's no way, each birth has a 50% chance of being a boy or a girl, right? So each of these results is equally likely. But if we wanted to know which among them, how many of them would be the same gender, all 3 children the same gender, and this statement is absolutely wrong. In reality, a girl is slightly more likely than a boy. That statement is incorrect. I one time worked with a neonatologist male, who said that we're all conceived female, and slightly less than half of us degenerate into males. So we all start off the same, and some of us change. So anyway, so among those outcomes, there are exactly 2 in which they're of the same gender. BBB and GGG. So 2 of those 8. So there's a 25% chance that if we had enough cohorts of 3 births that we were looking at, there's a 25% chance that over time that they would be same gender. Note here, same gender, not all boys or all girls, because there's only a 1 in 8 chance of all boys or all girls. So we're looking at a way of calculating these things using the classical approach, which is to look at the possibilities, calculate how many single events or how many subjective events can occur.
My coloring
Just
book
add them up.
and my marker in my book.
So this last one here is the subjective. Remember, the subjective is when we really don't have a basis for estimating a probability. So it's the probability of being stuck in an elevator. So people here, they talk about the possibility here, and of course, there are 2 possible outcomes when you get on an elevator. You're either stuck or you're not. Or you're not. So, but they're not equally likely. So we have to make an estimate, and that is just depends on our own biases. So these are when you see people making a lot of predictions, you need to know whether they're basing it on data. And what kind of predictions they're making. You know, the people that after the 9/11 attacks, we had a number of friends who just refused to fly. And, you know, objectively looking at that, that was not a rational choice. They were overestimating the possibility. And I can remember years ago when there was a spate of airline hijackings, we had a security expert come, because a lot of us at the company I worked for traveled a lot. And we had a security expert come in and he was talking about it. And he said, when you are hijacked, well, the number of planes being hijacked compared with the number of planes flying at any one time was extremely minute. It was maybe slightly more than the number that just spontaneously crashed, but it was very, very small. So he coming in and saying, when you get hijacked, implied something that was totally wrong.
Marker.
Here, there's a crayon in there. He needs his markers.
Yeah. So you need to be kind of careful. One of the things, look at the data that you're being asked to, and this is interesting here. The paper currency bills from 17 cities analyzed for cocaine contamination. So they were 23 of the bills they tested. 234 bills, and found that 211 were tainted by cocaine. So what you want to do is look at that and say, okay, it looks like
After school, I can help you.
it's all right. So it looks like an awful lot, over 90% of these things are contaminated.
Yeah, that's crazy.
That may or may not be true. Okay. Let's talk about the range of probabilities. The probabilities can be anything on a scale of 0 to 1 or 0% to 100%. A 0% probability is something that cannot occur. Example that they give is selecting a year at random and find the probability that Thanksgiving Day will be on a Wednesday. Okay. Well, the answer to that is 0 because Thanksgiving is always on Thursday. So the probability of it being on a Wednesday is 0. The probability of Thursday is 100% or 1. So probabilities always run in a range of 0 to 1 or 0% to 100%. They cannot exceed 100%. They can't be negative. You know, we look at that. I really get amused when I hear people saying, well, I always give 110%. Well, that's physiologically impossible. You can't give more than 100% of what you can give. It's just not a possibility. So those statements become meaningless in a hurry. Also, you see advertising that says, we've had a 100% reduction in something. Does that mean it's absolutely 0 at this point? Because the only way you can have 100% reduction is if now the rate of whatever that's going on is 0. An example here in the text is an advertisement by one of the airlines saying that they'd had 100% reduction in lost baggage. Well, that was absolute nonsense because there is no airline that doesn't lose baggage once in a while. So, you know, you can't, that would mean that they're claiming they're down to 0 lost bags. Maybe that was one day, but over time, that's not possible. So there are statements that are made using statistics that are not good. But that brings us up to the idea of the complement. Okay. We talked about rolling the die and getting a 6. And we said that the probability of getting a 6 is 0.167 or 1/6. Okay, 16.7%. The probability of getting anything other than a 6 is 0.833 or 5 out of 6. Okay, because there are 5 non-6 events that can occur with equal probability. Note that if you add up 0.167 and 0.833, it adds up to 1.0. So the probability of 6, P of 6, is 0.167. The probability of not giving a 6, which we call P of not 6, or the complement of 6, of the probability of 6, is 0.833. So we denote this by putting a line over. There's a couple of ways we can do it. We can put a line over the event. So in this case, we'd put a line over that 6 and a P parenthesis 6. Or we just call it not 6. I prefer not 6 personally. That's because that's the way I learned it. So the probability of not 6 is 0.833, which means if you're betting on a 6, you've got the odds are 5 to 1 against you. So if we go back to that smoker survey that was a couple of pages ago, then
yes.
No.
Then we have we have the complement of smokers is the difference between that 0.2 and 1, so it'd be 80% chance of a
Don't look at
non-smoker.
Not unless you're careful. Sorry.
Okay.
Mhm.
All right. All right. So we can, as I said, we can express these probabilities as fractions, decimals, or percentages. So on a scale of possible values for a probability, a 0 means that the event is impossible. It is not possible for me to go up on my roof and jump into the air and fly off. Okay, that's not going to happen. That's a 0 probability. In fact, there is a 100% probability that I'm going to fall to the ground. That is a probability of 1 or 100%. So there are some things that we can point to and say this will never happen. When we're talking about rolling some number of equal amounts in rolling a die, it's theoretically possible that I could roll the same die 100 times and get the same result every time. The probability of that is so minusculely small that is very, very unlikely to occur. And that's what we're looking at in this scale over here. Unlikely is anything down close to 0. Generally speaking, less than 5%. We call unlikely. And that's why this is placed where it is. This is about 5% of the total height. So anything less than 5% probability is unlikely to occur. So let's just look at things. This brings us up to calculating these probabilities. And so not going to go, we'll go in here to these unlikely and unusual events. So I've already said that small probabilities such as 5% or less or 0.05 or less are usually unlikely. But we have to look at the we can calculate some of these things using our classical test. We can also simply accumulate data by running a trial over and over again. And in that sense, that's what poker players do. Professional poker players playing with an honest deck and not playing with the current way that the casinos play, which is you get partially through a deck and then they can change it. So, and that's it with especially with black. So we have what we want to do is look at these things as an extreme result. Let's just say that again, we go back to rolling a die. We would expect if we rolled the die several times that we'd get a range of values. If we roll a die several times and we get the same value 3 or 4 times in a row, very unlikely and an extreme result, something that's far above what we'd expect. Now, if we do this because we can, if we do enough rolls, say we decide to roll the die 1,000 times, the chances are you're going to have 1/6, let's just say 1,200 to make it easy. If you roll the die 1,200 times, it's very, you will get very close to 200 of each value if you roll this enough. I say very close because there is still a possibility that you'll have 201 of one thing and 199 of another. That is actually a fairly likely outcome with that small a number. But if you went up to 12,000, you'd find yourself getting close to 2,000 of each, very close. Again, it might be 1,999 of one and 2,001 of another, but again, you can see that the variation is beginning to move toward that ideal value. So this again is the law of large numbers. But if we find that these extreme numbers are there, we can actually look at, remember z-scores from the normal distribution?
Yeah.
Okay, so the normal distribution, if you were looking at calculating a z-score, you would take all your data, calculate a mean, calculate a standard deviation, and then look at a data point to see how far, how many standard deviations it was away from the mean. And remember that anything over, anything outside a range of 95% of the data, remember, falls between two standard deviations above and below the mean. And what that means is that you're likely to find, you're going to find a few that will be there, but overall things will, you can calculate that probability. So z-scores can be used. This is one of the reasons we use our z-scores. We do expect in sufficient numbers of trials to have a range of results. Okay. So there's some questions here about probabilities. So we have a fair coin tossed 1,000 times, exactly 500 heads. The probability of getting 500 heads in the probability of getting exactly 500 heads in 1,000 tosses, and this is probably taken off of a normal curve of some sort, is 2.52%. Is the result unlikely? Is it unusually low or high? It's not unusually low or unusually high. You would expect that since there's a 50-50 chance of getting 500, or getting a head every time you toss it, then we would expect that. But if we only have 10 heads, that is an unusually low number, because we would expect something closer to 50-50 based on our classical interpretation. Two possibilities, 50% chance each time. So there should, in the long run, be equal amounts of equal result. So if we look at this again, if we did a lot of trials, this is something that we've probably was generated by a computer using a random function of some sort. But what they've got is, this is the number of heads in 1,000 tosses, and they've done a lot of these trials. So we've got, God knows how many tosses here, many thousands. So we are, this is 2 standard deviations away from the norm. So anything 468 or fewer is unusual. Anything 532 or more is also unusual. So we're looking at those. This obviously is where the standard this is 2 standard deviations above and 2 standard, or below and 2 standard deviations above. So it falls into that range. So the z-test, the z-score can help us. There's several other examples here that we won't go into because I'm seeing that you're going to be distracted off pretty quickly, which is reasonable. So let's not go into odds here because we're not really in those. Let us go into the next section. Okay. We have, this section is worth taking a look at, the addition rule, the probability of two things occurring at the same time, or one of two things occurring is that, okay, so to use the die example, if you roll the die one time, there is a 1 chance in 6 of a 6 coming up. But if you're looking for either a 6 or a 5, there are 2 chances coming up. So now you have your probability now has increased to 1/3 of being either a 6 or a 5. So this is addition of probabilities when you're looking at compound events, which is an event which has 2 or more simple events. Remember, simple event is one that you can't break down. So a simple event would be rolling a die, something happens. So, so here we have the probability notation is the probability, or P, of A or B. Okay. So we want to look at that. So this is where this drug screening that I mentioned comes in. We can look at this. The subject is using drugs, and he has a positive test result. And then there is 6 of them had a negative test result. Now, here we have 44 plus 6 is 50. 50 people who say they use drugs, and 950 who say they do not. So what are the chances that someone is not a drug user and tests positive? Well, he tests, there are 1,000 of them, and but only 950 are not a drug user, and 90 of them test false positive. So what we're seeing here is 90 out of 950 is going to be the probability that someone is both a non-drug user and then tests positive as a false positive for the drug. So that would be an example of why we would look at that. The other 50 claim to be drug users. So if we say, what's the probability of a drug user getting a false negative, that turns out to be 6 out of 50. A much higher rate of false negatives than false positives. So that's how we look at some of these, that's how we calculate these rates. So 6 out of 50 is 12%. That's one of the reasons that, and 90 out of 950 is less than 10%. So we have a higher rate of false negatives than false positives. This is one of the reasons that that drug testing comes under some scrutiny, and one of the reasons that even when you test positive, they'll confirm it. They'll use another test to confirm whether or not you have drugs in your system. This really affects people who are on chronic pain medications, for instance, like opioids. They often, when they apply for a job, and there are many, many reasons people are taking opioids, many of them quite legitimate. But we have to we have to confirm such things. So we have ways of doing preliminary testing. So so there's some information there in that section. We can have what we call, we want to look at events that are mutually exclusive. That is, they can't occur at the same time. We call these disjoint events as well. So if you were randomly selecting a person and asking about their political affiliation, they're either, most of them, the vast majority, are either going to be Republicans or Democrats. They're not going to be both. These are mutually exclusive events. And this is where, and then we have things that are not disjoint, meaning they can be both of something. And the example here is randomly selecting someone taking a statistics course and randomly selecting someone who is female. You're going to find a female, I've got one right here on the screen, taking a statistics course. So that's both. And this is where, remember the Venn diagram, have you ever heard of a Venn diagram? This is where you have a data set and an overlap. And the overlap is where they're members of both data sets. So that's one way of looking at this. When there is no probability, if they're disjoint events, then there's no overlap. Okay. So so that's where Venn diagrams become useful. So let's also look at this is sometimes the notation shown here on this page, this funny looking big, looks like a U-bolt between the two. This is in place of, this means one of the two, A or B. This is for disjoint notation. Sometimes this is symbolic logic notation for the concept of the probability of A or B. So for things that are not disjoint, we have the inverted U for A and B. So these are things that can occur at the same time, such as the female statistics student. So these things are, you have to be careful when doing this. This is here mainly for your information, but I'd like to get into something equally related, which is going to be the multiplication rule, which is that that this is how we can calculate the probability of events occurring over time. So when we have two possible events, or the events that we're talking about, we can actually multiply them together. If we are looking at as we said, the probability, and we can multiplication. Remember, multiplication is a simple way of adding numbers together, the same number repeatedly. So, but we're looking here where the probability of outcome doesn't have to be exactly the same. But we're going to stay with our dice for a moment. If we look at the probability of A and B occurring, this does not mean we're looking here at multiple trials. We're talking about the event A occurring in the first trial and B occurring in the second. sometimes they use this interpretation with this vertical line. When we look at the probability of B occurring after A has already occurred. So what we do is we multiply the probabilities together. So the probability of getting 2 6s in a row when you roll a single die are 1/6 times 1/6, which is going to equal 1/36, which is less than 5%. So it's actually pretty unlikely, even though it happens fairly often, for you to get 2 of the same number in a row. It's just not likely. And so we use those events as a multiplicative. So, and it gets worse if we have 1/6, to get 3 6s in a row, it's going to be 1/6 times 1/6 times 1/6, or 1/216. So now we're down to less than 0.5%. So a very unlikely event. Does it happen? Yeah. Any board game where you have a die to move your marker, you've seen it happen to you. Roll the same number several times in a row. Sometimes that's good, and sometimes it isn't. So they're independent if the occurrence of one does not affect the occurrence of the other. Meaning here, the occurrence of rolling the 6 the one time doesn't affect the probability that 6 will roll again. It just means that the coincidence of them rolling twice in a row is much reduced. So there's lots of information here. And if we go back to that drug test, we had among the 50 subjects who used drugs, with the total results of 50, we had 44 positive and 6 negative. So what happens if we look at that, we see that let's see. Two of the subjects are randomly selected. 2 of those 50 subjects are randomly selected. Find the probability that the first one had a positive and the second a negative. Well, we know that there is an 12%, an 88% chance of getting a person with a positive, of just randomly selecting a person here and getting a positive result, 88%, getting a negative result, 12%. But if we look at this, the second selection with 6 negative test results from the same 50, the negative is going to be 6. So the chances of getting the first as a positive and the second as a negative, we multiply those together. So again, that's going to be, that turns out to be about a 10.5% chance of that result. Now this without replacement and with replacement happens if you don't pull. If you don't replace that person, then the denominator now becomes 49, and we have if the first person is negative, there are still 6 false positives, or 6 false negatives. If there are 44 positives, and the person you pull out is positive, then there are still 6 false negatives, but there's only 49 people left. So the actual probability goes up slightly, very slightly. Does that make sense?
Yeah.
Sort of? Yeah. Well, just remember when you replace, this is a this is this has been put in here with respect to testing for drugs, but a lot of QA procedures in manufacturing will use replacement selections after they pull out a sample for testing for compliance with the QA procedures or QA established QA parameters. A lot of times they'll replace that one so that these statistics now become a little bit easier to deal with. If they don't replace it, then they've got one less in the pool. If the first one had tested as false positive, and if that's what you were after, if your first one tested as false positive, then you know that there are 44 positives or false negative rather. You know that there are 44 out of 50 false 44 out of 50 positive results left. If you don't replace it, it now becomes 44 out of 49. So this number just changes a bit depending on whether you replace or don't. There's a whole science of that. This is something I've always suspected at airports when they weigh baggage, if their baggage scales are defective, if they read high. Because especially when we go visit one of our kids overseas, there are pretty strict limits on baggage weights. And we weigh things pretty thoroughly before we take off to the airport to be sure that we're underweight. And they've told us before, oh, you're a kilo over. Well, we were 2 kilos under at home. Now, I don't believe our scale is that bad. So I've wondered about this. But if we look at this, we look at 102 scales out of 810 at New York, the 2 big airports in New York City. That's a lot. That is in reality about 12% of the scales being defective. So again, we can calculate these numbers. The chance that both of them with replacement are going to be defective is 102 out of 8 divided by 810, and their times, again, 102 out of 810. So we get a chance, a probability of 1.59%, whereas if we don't replace it, it drops to 1.57%. And again, what is this? A larger population of 10,000 scales includes exactly 1,259 defectives. So if we take 5 of those without replacement, we're actually, again, reducing the denominators. In other words, it's very, very unlikely. It's also a cumbersome calculation. Does that make sense?
Yeah.
Okay. Let's keep going. Go ahead.
Mom.
There was one thing about so we reduced the denominator, but not the denominator, right? Like not the top number, correct?
Right.
Mom.
Yeah. Yeah.
Okay. Well, that one back there, the baggage one, reduced the top number. Why is that?
Well, if we go back here, what we've done is without replacement, if the first one is defective, we've knocked out one. Two. We've knocked out.
Okay, so we reduced the denominator as well too.
Yeah. So if we are not replacing, if we are replacing, we get a first defective and we replace it, then the denominator and numerator remain the same. But if we are not replacing and we've got a defective one, then we only have 101 defective ones left. and only and
Oh, okay.
809 total. And the same down here with the 1,259 out of 10,000. Every time if we have a defective one, then we've reduced that. If the next one wasn't defective, then what we've got is a different number. This number doesn't change. This becomes now 1,259 out of 99.99 because we haven't taken out
Okay.
a defective one. Okay. That makes
Okay.
sense? Yeah.
Did you eat dinner?
It's a little bit of thinking. Okay. Okay. And there's
Yeah.
some other examples here.
Did you eat
All
all
right.
your dinner?
Yes.
Well, I'm gonna need to go confirm
Let's keep
before you have a
going.
Pop-Tart.
Huh? What, Mom?
This
What?
one,
Get out of here.
I don't want to get out of here. I just want to stay here.
Okay, keep going.
okay. So there's a couple of other examples here that you may want to look at. Here we're looking at a tree diagram of a procedure here. Okay. Random guess, and we're talking about randomly guessing answers to a question. Okay, so we've got we have a question, two possible answers, true, false, and so this is how they're set up. That you can make guessing either very, very difficult. If you have straight true false, let's go back a page to what the questions are here. A pound of, question one, a pound of what we've got is there are true, false, and a multiple choice question with 5 possible answers. So what are the chances of getting of a score? The first one, a pound of feathers is heavier than a pound of gold. That's true or false?
Or false.
That's right. A pound is a pound. Yeah, feathers individually
Right.
are lighter, but a pound is a pound. And it just happens to be that a pound of gold is about this big, and a pound of feathers is going to probably fill up half my office. So
Yeah.
size doesn't matter.
Yeah.
That wasn't it. And then who said by a small sample we may judge the whole piece, and there's 5 choices. So here's the tree of the possible scores that the test taker could have. They could miss the first one. They could be right on the first one, and then they have a 1 in 5 chance of being right on the second one, just randomly guessing. Now, if they know the answer, then random guessing doesn't count. But if they didn't have a clue and they randomly guessed, that would be it. Or they could miss the first one. They could say that that's false, that a pound of feathers is not heavier than a pound of gold. And then they still have the same, again, random choice, random guessing, 1 in 5 of getting the right answer. So we can actually calculate what the scores would be. So we can calculate the probability that both are correct. Or we could go back and make a new diagram and calculate what a score is. So we can calculate our probability of coming up with getting both of them correct, which is they've got a 50% chance of getting the true false correct and a 1 in 5 chance. So a half times a fifth. They've got a 1 in 10 chance by random guessing, only a 10% chance of getting it right. So this is why we don't like people to guess on tests unless they can eliminate some of the multiple choices, right? You get it down to a either or, your probability goes up. But that requires that you know something about it. So, okay. So we can look at that. We don't want that. Want to get quickly to, let's see, counting. Let's go here. Permutations and combinations. You've looked at the Khan Academy video, so you've covered some of this. Permutations are arrangements in which different sequences are counted separately. If we look at license plates, and a license plate starting CBA is different from a license plate starting ABC. It doesn't matter if everything else is the same. So CBA and ABC are different. In combinations, CBA and ABC are considered the same. Okay, so that's the major difference between permutations and combinations. So the combinations, permutations of the letter ABC means how many different arrangements can you make? Okay, so, and in combinations are just how many combinations can be put together, meaning if you had the alphabet, how many combinations of 3 letters, irrespective of order, could be put together. So, in other words, again, ABC is the same thing as CBA. So anything involving the letters A, B, and C would be considered the same combination, but they are different permutations. Does that make sense?
Yeah.
Okay. So how do we do the calculations? Well, we can simply calculate, but I'm going to put up, there's a couple of things. You've seen factorials. Factorials figure in here very, very strongly. So permutation rules. Let's just take a look at the number of 3-letter permutations are available in the first 5 letters of the alphabet. So there are 5 letters here. Okay, that's our basis. We are told, and that is in this formula, that's N. So the P in this case does not stand for probability, it stands for permutation. This is one of the problems in math. You're going to find a number of times when the same symbol is used for different meanings. So that means you have to understand the context. Okay, so if we're going to have these 5 letters, then this N at the beginning of P, at the beginning of this notation, tells us that there are 5 items that you're going to calculate permutations. R is the number of those items that are going to be selected. Okay, so without replacement, we're just going to say that's without replacement. So again, we're leaving out the possibility of AAA, ABB, etc. So in this case, we're going to do a permutation. So the formula for that is n factorial divided by n minus r factorial. In this particular case, it's going to be 5 minus 3 factorial. 5 factorial divided by 5 minus 3 factorial, or 2 factorial. Now, I'll just give you a quick rundown here. We can have when we're doing this calculation, this is 5 times 4 times 3 times 2 times 1, right? Okay. 5 minus 3 is 2. 2 factorial is 2 times 1. We can simply cross out the 2 times 1 from the numerator and multiply 5 times 4 times 3. And that gives us 60. 5 times 4 is 20, times 3 is 60. So what we do is we do this first, and then we just take out the rest of it. We could put this up as the entire alphabet. 26 factorial. That sounds like a big number, and it is. It's gigantic. but it's divided by 26 minus 3 factorial, or 23 factorial. So then we would have 26 times 25 times 24 times 23 factorial, because 23, etc., is 23 factorial. 23 factorial would be our denominator. Cross it out. You have a simple much simpler calculation of 25 times 24 times 23. Does that make sense? The math becomes easy if you set it up that way. You can also, scientific calculators, and I think our computer calculator have a, let's just take a look. I happen to have my calculator. We have, we don't have the, n factorial. So
Wait, you have to share your calculator too.
I'm sorry. You bet. Sorry. Oh, Lord. How can we do? Oh, here we go. Is that there? Is it there now?
Yep.
Okay, good.
Yeah.
I keep forgetting that. So we do have n factorial. So you can use the computer calculator. I know my phone calculator doesn't have it in its scientific notation. So, but it is available in these things. Okay, so I'm going to shrink that down. Are you still on the page here with the problems?
Yeah.
Okay. So there are some other things here, like more complicated permutations when some are identical to others, like license plates, because AAA is different, can be used, and ABA, AAB, BAA. These are all, we can replace those letters if we take them. So if we have, if we have the, we can calculate that. We're not going to go into that for the simple reason that that I don't want to get into to big calculations, but we can do these things. Combination rule is different when order doesn't count. And again, same thing. C is the symbol. N is the number of choices. R is the number of selections that you're going to take. But the denominator becomes different. We have n minus r factorial times r factorial. So let's take a look at, since the same question, how many combinations of 3 of the 5 first letters of the alphabet are possible. So we have n is 5, r is 3. So we substitute then in 5 factorial times 5 minus 3 factorial times 3 factorial. So that becomes 2 factorial times 3 factorial, which is going to be 2 times 1. And 3 factorial is 3 times 2 times 1, or 6. So we've got 120 over 12. So now we've gone from 60 permutations to only 10 combinations. So combinations do not allow view any set of the same 3 letters as identical. So again, AA or ABC is the same as BCA, etc. So that's how we calculate this combination. This is when we have things that are identical, so we won't go into that. This N1, N2, NK would be the number of A's, the number of B's, the number of C's, the number of D's, and the number of E's. D and E are both 1. 1 factorial is 1, so they just didn't put them in there. So that's how we do when some of these items can be identical to others. Okay. So let's go on. We'll look at this. Wait a minute. Needed to go down a page. Okay, we won't go into horse racing. Um, a Again, we can have arrangements. Okay, if someone were to put 6 presidents in chronological order, something I'm not sure I could do, to tell you the truth. But anyway, there are 720 different possible arrangements, because there's 6, 6 times 5 times 4, etc. So the chances of being able to guess the answer is, less than 0.1%. So we can calculate a lot of different things this way. Let's see. We're not gonna go into too much. I'm trying to remember. Oh yeah, there are a couple of things. Does order matter? Permutations and combinations. If we look at this corporation, it's going to appoint a president, a CEO, and a COO, and a planning committee with 3 different members, 8 qualified candidates, and officers can be put on there. How many different ways can the officers be appointed? Order doesn't count. So we have 8 people, and we want 3 of these people to be appointed to these 3 offices. So we have, the N here is 8 and the R is 3. So we have 8 factorial over 5 factorial. And when we carry out that calculation, 336 different permutations where we could come up with the 3 officers. But order doesn't count when we get combinations of people selected from, and this is in the committee. Doesn't matter what the order doesn't count. So the committee is just these combination of 3. So again, we have 56 ways of putting 8 or 8 people, planning committee, 3 people onto a planning committee. So there's 56 ways we can do that. But when since we have any combination, if we're feeling that our CEO, president, and COO are all equally, our candidates are all equally qualified. So the combination of the 3 doesn't matter, and we're not replacing them in the count. And so the combination here is for the committee. However, it doesn't really matter. Everybody's qualified to be on the committee. So you're not taken out of the pool if you're appointed to something else. So this is one way of looking at this. Do corporate executives or anybody that's doing this kind of work go through that kind of thinking? No. As a rule, they won't. But you just need to know that there are lots of possibilities. Okay, let's keep going, see what's left here. Let's see. I think we're at the end of this. Okay. Yeah, I think this is about it for today. I'm getting worn out. It is 8 o'clock. So questions? Let's go back.
No.
Okay. Well, you can. I will not claim that I will be online a lot tomorrow because I'll be traveling. But I will check my email when I get settled into the apartment tomorrow night, and get back to you if you have questions. Let's plan on meeting at 6 on Thursday, your time, 6 o'clock your time.
Okay.
I will send you
Go
go ahead.
What's your time out there? Is it later or earlier?
It'll be later. It'll be 8 o'clock my time.
Oof. Do you want to start earlier? I don't think that I would have a problem starting earlier. I do have to go back to work tomorrow, but maybe I could just email you. Maybe we could start at 5 if you want.
We can try, and it's going to depend. I mean, 5 is 7. It depends on what I'm doing with my family. Why don't
Okay.
Why don't
Well,
we
you let me
plan on
know what works best for you.
that? Okay.
I just don't want
I'll
it to
get
be
things
too
set
late
up.
for you. I mean,
No, that's not that late. I mean,
okay.
I generally stay up late anyway, and probably get up too early, but yeah, it's not too late. But yeah, let's look at that, 7 p.m. or 8 p.m. You probably don't like to go much later than this. Is that right? Or would it be possible for you to start even at 7? It's up to you. I know
No,
you have
it would be
have a
possible.
son to
I can
take
start
care of.
whenever.
Okay.
Yeah,
Then,
I know. But my mom helps me out a lot with that, so it's not a problem. Whatever works best for you, I can be flexible too.
thank you. I appreciate that. Then let's plan on that, and we'll do another class on Tuesday next week as well.
Okay.
And then hopefully you'll have some transportation for the last day of class. We can actually meet face to face for a change.
Yeah.
Okay. Then
Yeah.
in that case, let's plan on that. Go ahead and get started. We'll discuss regression. It might be a shorter class Thursday. Regression analysis is a little easier to deal with. I think it'll be a shorter topic
Okay,
than all the
good.
background we went through tonight. So we'll work on that. All right.
Yep.
Okay.
Yeah.
We'll end here, and I will see you on Thursday night.
Okay. Well,
Okay.
thank you, Mike. I appreciate all your help.
Oh, you're welcome.
And
Glad to.
safe travels, okay?
Thanks a lot. We will
Yeah.
plan on safe travels. Okay.
Yeah.
Bye now.
Definitely no plane crashes. Bye now.
No.